Welcome to this UCL lunch hour lecture on catalysis, fundamental science supporting industry, energy, and the environment. For those who don't know me, I'm Miss Basawa and I'm a computational chemist at Johnson Matthey. Our speakers for today are Professor Richard Catlow and Professor Andrew Beale. Richard Catlow is Professor of Materials and of Computational and Materials Chemistry at University College London and Cardiff University. He's a Fellow of the Royal Society, a member of the German National Science Academy, the Leopoldina, and of the Academia Europaea. He served as head of UCL Chemistry from 2002 to 2007, Dean of Mathematical and Physical Sciences from 2007 to 2014, and as Foreign Secretary of the Royal Society from 2016 to 2021. His research program is based on the development and application of computational techniques used in direct conjunction with experiment in probing the properties of complex materials. Andrew Beale is a Professor of Inorganic Chemistry and Group Leader at the Research Complex at Harwell. He is also a Management Group member of the EPSRC-sponsored UK Catalysis Hub. His interests lie in establishing structure-function relationships in materials, including catalytic solids and energy storage as a function of both time and space, using X-ray and optical spectroscopy and scattering methods applied under in situ and operando conditions. In 2012, he co-founded Finden Limited, providing high-end characterization of solid-state functional materials spanning the fields of catalysis, energy, automotive parts, and pharmaceuticals. He's published over 200 papers. Before we begin, I wanted to let you know that we will have some time at the end of the lecture for questions, and these can be submitted at any point during the talks by going to slide.do, which you enter into your internet browser, and entering the event code #UCLScience. I will now hand over to Richard and Andrew for their talks.
Thank you very much, Ms. Barr. Good. Well, thanks very much for the invitation to speak at this lunchtime lecture series. What Andy and I think, are hoping to do today is really perhaps two things. Is first to show how fundamental science has developed over the years into powerful tools for applications in industry. And secondly, to show the absolutely key importance of catalysis in the economy and indeed in society in general. But anyway, first, what is catalysis? Well, here I'm attempting a definition. It's a process whereby chemical reactions are accelerated by a reagent, that's the catalyst, that isn't actually consumed in the process, although it may be and often is degraded. And then just a few basic facts about it. It is the basis of the chemicals industry. We couldn't have a chemicals industry without catalysis. And there's a figure here, underpins over 200 billion of UK GDP per year. It's absolutely vital for the simplest, for all but the simplest life forms. And the fact that I'm speaking to you at present is because chemical processes catalyzed by enzymes are taking place in my body. And it's essential for the nutritional needs of the majority of the world's population. We could not support the current global population without catalytic science. Now, it's a molecular process, and here is one absolutely vitally important example. This is nitrogen fixation, a very simple piece of chemistry. I'm going to try and not to burden you with much chemistry, whereby nitrogen reacts with hydrogen to make ammonia. And one of the milestones in catalysis was in 1910 when the Haber-Bosch synthesis process was developed. It's a catalytic process. And we now know how it works. It's rather simple chemistry. The catalyst, as you can see in the graphics here, prizes open the nitrogen molecule into two nitrogen atoms, and hydrogen atoms are then added to it to make ammonia. And I just mentioned a minute or two ago about the importance for the global population. Well, there is a reliable statistic that we could not support half the world's population if it weren't for nitrogen fixed by this process. So the Haber-Bosch process allows us to support half the global population, the nutritional needs of half the global population. Now, my work in catalysis has been all about trying to understand catalysis at the molecular level. That's the fundamental challenge. And what do we need to understand? Well, we need to understand the structure. Perhaps if catalysis is taking place on the surface, that's what we call heterogeneous catalysis. We need to know something about the surface structure. We need to know the structure of the active site. The catalytic process will take place at particular points, say on a surface or within a solid. And we need to know that structure. We need to know how molecules get to and from the active site. Once they're at the active site, we need to understand the reaction mechanism, how the molecules rearrange and bonds are broken and made. Then we need perhaps to understand how we synthesize a catalyst, and then, of course, how they can evolve and deactivate. Now, what I'm going to argue is that by developing this understanding, we can optimize catalysts and design new ones. And there are good examples where this has taken place. Now, my speciality throughout my career has been computer modeling. And computer modeling is a powerful and essential tool for gaining this understanding. Now, just a word about modeling. I said I've been involved in modeling throughout my career. And early on, people kind of wondered what this computer modeling was all about. And in fact, I've argued, and I think it's now accepted, that computer modeling is just a modern form of what scientists have been doing for thousands of years, that is building models. And why do we want to build models in science? It's because they scale objects and processes to size and time scales that we can understand. They can take us from unimaginably small things like atomic nuclei to unimaginably large like galaxies, and for incredibly short time periods to incredibly long. And that's really the power of modeling. On the left-hand side here, you see actually a model of galaxy formation, marvelous work of Carlos Frenk, a good friend of mine at Durham University. But let's just think a bit more about computer modeling. And I argue that it bridges theory and experiment, because the fantastic achievements of science over the last few hundred years have allowed us to understand the fundamental factors which control many physical phenomena. We now have a lot of information about the forces between atoms, and this allows us to do what we call molecular mechanics, to predict how structures of collections of atoms, molecules or solids. We understand the basic theory of electrons in atoms, that's quantum mechanics, so we can understand how chemical bonds form and break. Now, if you look at other areas of modeling, interactions between planets, stars, and galaxies, that's driven by gravity and relativity. And we understand the basic theories of fluid flow. So we can feed all this information into can exploit the power of modern computers. And this allows us to use this theory to construct models of complex real systems. And we've done that in catalysis. This is a model of what we call a mesoporous silica catalyst with metals deposited on the inside. And that was developed by colleagues of mine at the Royal Institution. Now, let's just think about how computational catalysis has developed impact. Now, if we go back to the early days, perhaps in the late 70s, 80s, and the 1990s, UCL-RI and other teams, I should say, around the world developed the modeling tools that allowed us to understand catalysis at the molecular level. And they show that they work. And that was funded largely by research councils, but also industry. Johnson Matthey have been generously supporting my research program since the late 1980s. Then I developed, or my group developed, collaborations with the Daresby laboratory over the development of a very powerful piece of software, the ChemShell code. I'll say a few words about this, more words in a minute. And then I think significantly, I developed a collaboration with a SME, Biosim, which changed its name then to Catalysis, I was one of the scientific leaders for a consortium that they developed to provide software for modeling catalysis, to take the kind of basic software that had been developed in the university teams and adapt it into user-friendly and widely applicable software. And that was a very successful project, and it made these tools available to a wide range of both academic and industrial users. And then we start seeing the applications to real industrial problems. And I think Johnson Matthey has been an absolute leader in using these techniques for real problems. I just finally note here that several of our PhD students, including our distinguished chair, did their PhD in the UCL RI teams. And that's, again, another, I think, important type of impact. This is just a word about this ChemShell code, a very powerful piece of software. It's based on a simple idea. You use powerful, really powerful theoretical methods for a kind of inner core region. If you're modeling a solid, that's where the catalysis takes place. And then you describe the more distant regions further away by rather simpler methods. It's a simple idea, but a very powerful idea. And my group has worked with the Daresbury team now for over 20 years developing this software. Now, sorry, this is a rather crowded slide. I just wanted to go through, perhaps in rather general terms, some of the ways in which this computational method work has had impact. And I'm listing here, and most of these actually are statements coming from Johnson Matthey. The collaboration between UCL and Johnson Matthey in strategic areas, including fuel cell formulation, sustainable hydrogen production, has all profited from these computational modeling studies. They provide unique and novel insight into an important catalyst, a syngas catalyst. And this is a quote where we, Johnson Matthey, have needed to go beyond intuition to make significant advances. The ChemShell software that I've just mentioned was applied to what we call self-catalytic reduction. I'll say a few words about that in a minute. And has helped Johnson Matthey to become a market leader. And fundamental understanding of these zeolite catalysts, I'll say a few words about zeolites in a minute, again, has helped to optimize this key catalytic process. Now, here actually is one example. This was work done by my group. It's done by a PhD student, Sarah Khan, in collaboration with Johnson Matthey scientists. It included Sam French, who again had been a Royal Institution student, now a senior business manager in Johnson Matthey. And it was a piece of basic science. It looked at how cerium, a metal, can dissolve into this lanthanum cobalt oxide material, which is a powerful catalyst for a range of catalytic processes. And we worked out using modeling the kind of ways in which this cerium could be accommodated in the catalyst. This was a piece of fundamental science published in the Journal of Physical Chemistry. But Johnson Matthey, I understand, were able to use these to optimize this fundamental knowledge to optimize this catalyst, and it really had commercial impact. Now, let me say a few words about these zeolites. I'm sure Andy's going to tell you more about them later on. These are absolutely fascinating materials that, again, I've been interested in almost throughout my career. They're silicate or aluminosilicate system. So the basic building block is silicon surrounded by 4 oxygens, making a nice tetrahedron, or you can have aluminium surrounded by 4 oxygens. And then you start to fit these together by the sharing corners. And in this case, you can generate these beautiful structures containing cages, pores, and channels. And they're beautiful structures, but they have a lot of very important applications. They can be used in separation technologies. The channels can act as kind of sieves, and you can separate molecules with different sizes and shapes. And separation technologies, very important in the chemicals industry. But perhaps the biggest and most important applications are in catalysis, because they contain active sites within them, metal or acid active sites, and they can do all kinds of catalysis, particularly catalytic processes that are important in the petrochemicals industry. Actually, a more traditional application is in ion exchange, so they're used in water softening, but we're going to focus on their catalytic applications. And here's just one. I mentioned this SCR process, and this is a process whereby these very unpleasant nitrogen oxides in heavy-duty emission exhaust are removed by this catalyst. So this is really important for environmental control. And the catalyst that's currently used, the most widely used catalyst, is one of these zeolites. You see the cage structure there. And what we do, you see the chemical reaction here. The ammonia reacts with NO, these unpleasant toxic gases, and the reaction involves the formation of nitrogen and water. And the catalyst used, as I said, is this cabazite, zeolite cabazite, and it has copper ions exchanged within it. And it's the copper ions that provide the active site. Now, just a word about work that's actually in progress here at UCL. One of my students, Jamal Nasir, working together with Andy, has tried to understand the kind of fundamental mechanisms of this catalytic process. He looks at copper ions inside this zeolite. He looks at how they react with the NO and with the ammonia. He looks at all the intermediates, and he's pieced together, I don't expect you to follow this slide, he's pieced together a full cycle for the catalytic process. This is work that's just been completed. And this, again, this fundamental understanding will allow us to improve these catalysts. Now, what I want to do now is talk about some of the current challenges, rather briefly, and some areas where I'm sure they're going to be future impact. I'll talk a little bit about what I call the CO2 challenge, about a circular plastics economy. I won't have time to talk about biomass utilization, although it's crucially important, but I will talk a bit about greener ammonia. Now, a word about the plastics challenge. I'd like to thank Matt Davidson from Bath University for letting me have these slides. It is a huge challenge. Here's just some statistics. 1 million plastic bottles bought globally every minute. And then each person on the planet will generate twice their body weight of plastic waste every year by 2050 if we continue the business as usual scenario. Here are just some more statistics about comparing to the plastics in the environment in 2014 with 2050, and probably just concentrate on the second one down there, the ratio of plastics to fish in the ocean by weight. And 2014 it was 1 to 5, so the weight of the fish was 5 times that of the plastics. The business as usual scenario said there'll be the weight of plastics in the ocean will be the same as that of fish in 2050. So again, it brings home the scale of the problem. There's a lot of data on this slide here, and I just want you to concentrate on the figure on the bottom left-hand side, because that shows the projected increase in plastic production in different regions of the world. And look at the bit in yellow, that is the Middle East and Africa. Now you see at present it's pretty low, but it increases to be probably the biggest, this is the business as usual scenario, the biggest quantity of plastic production will relate to Middle East and Africa. And this makes a very important general problem, that we will not achieve global sustainability unless we look at what's happening, particularly in Africa, where the population is going to double in the next 25, 30 years, and where there is rapid economic expansion. Anyway, this is what we've got to move to in plastics. We've got to design and produce them, we've got to use them, but then we've got to recycle and reuse, and only a small amount going into the environment. Now, that's not what we do at present. And to do this, there are technical challenges all the way along the road, and we will need catalytic processes for enhanced effectiveness. We need energy efficient processes, they need to be robust and benign, we'll need self-healing materials, we'll need program degradation and chemical recycling. All these are challenges for catalysis. Now, the CO2 challenge, I'll be very brief here. We all know of the issues relating to climate, so I'm not going to say anything more about that. But I do want to say a couple of words about CO2 as a carbon source and the importance of sustainable hydrocarbon fuels. CO2 will be needed as a carbon source in the post-fossil fuel area. We're all using and wearing products made out of carbon. Those are coming from the chemicals industry. The sources of carbon for the chemicals industry are at present mainly fossil fuels. That cannot continue. We need other carbon sources. CO2 and biomass will become carbon sources. And then CO2 hydrogenation, the reaction of carbon dioxide with hydrogen, will be needed to produce fuels and chemicals. For example, aviation fuel will almost certainly need hydrocarbons, certainly for long haul flights, and to develop sustainable aviation fuels, we will need to develop efficient CO2 hydrogenation catalysts. Now, let me say a few words about the ammonia synthesis and towards a greener ammonia. And I'll highlight work here of Konstantinos and Alipur Yazdi, who worked in my group here at UCL a few years ago in collaboration with Justin Hargreaves at the University of Glasgow. And again, this is the chemistry we're looking at, the simple chemistry, the reaction of nitrogen, molecular nitrogen with molecular hydrogen to form ammonia. And as I said, an absolutely key process. And at present, we have to do this at high temperatures and high pressures. It's a sluggish reaction, and we really need to force the chemistry to happen. And that means it's pretty energy intensive process. Now, can we do something cleverer? Well, again, I showed this slide before. This is what the Haber-Bosch process does. It prizes, the catalyst prizes open the nitrogen molecule. And that's why this is such a difficult chemistry. I sometimes call it sledgehammer chemistry, because nitrogen, the NN bond, is just about the strongest bond in chemistry. And what we're doing here is we're pulling nitrogen atoms apart. We're having to break that very strong bond. Can we do something cleverer? Well, I will argue that we can, and this is what Konstantinos showed. Justin Hargreaves, who we collaborated with, has showed that this compound, cobalt molybdenum nitride, actually could undertake this catalytic process under more mild conditions. And what Konstantinos was able to show is that this catalyst could trap a nitrogen molecule on its surface and then could start to add hydrogen atoms to the nitrogen molecule before you break that very strong bond. And you degrade that strong bond into a weaker bond by adding hydrogens, and then you break it. So this is what we call a non-dissociative mechanism. And we think this is the key to getting greener ammonia synthesis. Now, just before I finish and pass over to Andy, just a few reflections. To achieve maximum impact, I think we need to do a lot, but here are three things we need to do: exploit the latest techniques and infrastructure, use all the digital capabilities, and collaborate and coordinate. And here's an example of collaboration. The UK Catalysis Hub, Andy and I are both very heavily involved in. It's a consortium of over 40 university groups, and currently it has the structure shown here, three main themes. I'll not go through them, but the point I'm making is that this has proved a really effective mechanism for collaboration, for bringing groups together throughout the UK. And this is what we're going to have to do to develop the impact that we need. Here's an example of technology. This is the Archer 2 National Supercomputer System, fantastic piece of technology at the Edinburgh Parallel Computer Centre, and it is being used very effectively for computational catalysis and many other things as well. And here it's the aerial view of the Harwell Science and Innovation Campus, where we house our major facilities, the ICIS Neutron and Muon source, the Diamond Synchrotron source, the central laser facility, all of these being used very effectively for catalytic science. And on that note, I will pass over to Andy. Let me stop sharing my screen. So over to you, Andy.
Thank you very much. And I will now try and share my screen. So I assume that's right. No one's complaining at this point.
That looks good.
Thank you, Ms. Barr. Yes, and thank you again, Richard. A good point there to finish. So my first slide is again a perspective from the Harwell campus from the other angle. And I've highlighted what Richard pointed out at the end of his talk. Let me just see if I can get a pointer there. Basically, we have this ring state structure here, which is the diamond light source, and then we have central laser facilities and the ICIS neutron source. And what you can see here in the top right-hand corner are some other organizations that have a footprint on the Harwell campus. I'd like to point out particularly Johnson Matthey, because one of the collaboration between UCL and Johnson Matthey has led to greater engagement of Johnson Matthey with these central facilities. So these central facilities are government funded to the tune of, particularly the Harwell campus, something like £150 million a year. But about 5 years ago, Johnson Matthey contributed to the building of this center here. So this is the Electron Physical Sciences Imaging Center, and this was a joint investment from Johnson Matthey and SCFC. So that's the funding council that's responsible for budgeting or spending the budget, for example, on these facilities. The good thing for UCL employees, in fact, anywhere in the country, really, I mean, it's only 60 miles from London to get here, so it's only about 1 hour on the train. But actually, I'm based here permanently because I work a lot with Catalysis Hub, which is also housed in this building here. And we have a startup company that was started about 10 years ago. So it's its 10th anniversary this year, which is also on this campus. So in fact, as you'll see around the campus here, there are quite a few other buildings, and that's a bit of a mixture of UKRI funded capability as well as private enterprise. So this Harwell campus actually houses several thousand people, about 3,000 people. So mainly because of the presence and capability of these facilities. To look at indeed, materials properties, be they biological or physical. So what I'm going to focus on today is primarily synchrotrons. So synchrotrons are very bright light sources. The UK invests in 2 of them, primarily synchrotrons. So the diamond light source that you saw in the previous slide, and this one here in France, near Grenoble or in Grenoble, called the European Synchrotron Radiation Facility, so ESRF. Why are they so useful? Well, if you look here, this is the emission profile of a synchrotron, and we compare the emissions, and what we have here is the photons, if you like, per unit area per second. And then we have what's known as kind of an infrared lab source, so basically an infrared instrument that you might find in a typical lab, and also with a X-ray source, a molybdenum X-ray source. And the key thing you note here is that this emission from the synchrotron is not only more intense, but it's continuous. So you actually have the ability to tune or choose a wavelength to study a material of interest. And in particular, some of the beamlines or some of the facilities, and I'll show you a beamline in a minute, actually have incredibly bright sources, or in fact are incredibly bright sources. And that allows us to interrogate samples with either nano beams, because obviously we trying to get, when you get a very small beam size, you often lose some of that intensity. But of course, if you've got a lot more to start with, you've got a lot more chance of imaging something small, or of course with a high time resolution. So here we're talking milliseconds, microseconds, or even faster. So they're very versatile facilities. And the other thing that they're very versatile at is that we can create a sample environment to actually study material in its, let's say, near as possible native environment. So what we've particularly focused on over the last few years, so this is primarily myself, but also in collaboration with Professor Catlow and Professor Sanker from UCL, is actually studying materials as they do something, and having this infrastructure is critical. So not only are there bright light sources, but there's plenty of space to mount a sample environment, to create the environment that we're wanting to study the material in. And typically what's not shown on here, but you will see the results of later on in this presentation, are these very sensitive detectors. So they're state of the art. They are very sensitive, able to process a large volume of data within a very short time frame. Now, one of the philosophies that we have when we study materials is that we want to actually verify they're doing what they're intended to do. So in order to verify that they're doing what they should be doing, we have to actually do what we call operando measurements. So for catalysis, that means that we take our sample and put it in a microreactor, which is just a very scaled down version of what's used in an industrial setting. And then what we do is that we pass our reactive gas over the catalyst, and then we convert it into a product. But what we're doing when we're doing a measurement with the X-ray source, so we might be looking at how, for example, the molecules in this gas react with the surface of this catalyst that Prof. Catlow identified as being so important. And then we're trying to see how that material responds. And if we understand how it responds, we are able to design either more stable or better performing materials. And how do we do this? Well, once we measure this change, So here, this is an X-ray absorption spectrum that's been kind of converted into a distribution function. So we can see some intensity with time on stream. So after 7 minutes of reaction, we see this increase. Well, basically, we can actually show that 7 minutes into reaction, when we're monitoring this outlet, so as the catalysis is taking place, we can sort of see that 7 minutes seems to coincide with the formation of a product of interest, in this case, benzene. So linking those two things together, we get these more detailed structure activity relationships. Now, in 2012, as I mentioned before, the company Finden Limited was created. A colleague of mine and I created this company. This was effectively built off some research we did whilst at least one of us was at University College London, but at some point both of us had worked at UCL. And it was mainly to help businesses fast track their R&D. So we were finding a lot of customers, or at the time they were just companies, wanted to understand why their materials worked or why they didn't work. And a key thing is that in industry, timescales are a lot tighter than what they are in academic research programs. So normally we talk about turnarounds of days to months, whereas of course in academic research, it's important to actually get things well understood. So therefore it takes a bit longer. The company actually now comprises 10 people. There's one face missing off here, but trust me, there's 10. So what we have is a mixture of skill sets that complement our business. A key thing is that practically everybody on here, no, except two. So Stephen Price and Panos are all ex-UCL graduates, or undergraduates in some way, shape or form. So this has been very beneficial for us, because for us to grow our business the size it is, we've needed some high quality talent. And obviously UCL is a good source for this. And one of the key developments I highlighted before was some of the research that actually drove the creation of our startup was the technique that we created called X-ray diffraction computed tomography. Now, we're all very familiar with powder diffraction as a technique for characterizing solid materials. But the problem is when you're measuring a sample, even if you're trying to do an Operando measurement, is that you're typically taking one part of the sample. But we know that by accident or design, the best functioning materials are often heterogeneous. So how do you interrogate heterogeneity in a process, and to understand the impact of that? Well, you need to do spatially resolved measurements. So what we did was we effectively amalgamated X-ray diffraction with computed tomography. So computed tomography is a familiar technique to us all because it's typically used for medical imaging as a non-invasive technique for effectively identification of abnormalities inside humans and animals. But of course, there you only get a black and white contrast image. By putting XRD and computed tomography together, we are actually able to look at the crystalline distribution of species in 2 and 3 dimensions. So what we have then is a diffraction peak, let's say, for a particular phase, which we then reconstruct into a map. And so here, within these particles, you can see that the nickel has a greater intensity towards the edges. So we have a scale bar here. So the more red something is, the more intense the signal. But you can see in most of these samples, there is a congregation, let's say, of the nickel towards the periphery of these particles. So it's a very powerful technique, say, developed while some of us were working at UCL. Nowadays, we've moved this on. So in the previous image, which was just a cross-section through a portion of the sample, now we can actually do lots of measurements as a function of height. So that's illustrated here in a catalytic reactor. So now we're actually able to probe not just the 2-dimensional variation in the particles, but a volume information. And what that basically, how that's been enabled is that synchrotrons have a very, very high brightness of X-rays, as I mentioned early on in slide 2, particularly at certain energies. So we get this very, very high brightness, which can pretty much go straight through more or less anything. Well, obviously, depending on how thick it is, but typically the sort of micro reactors that we use. In fact, I would say these are micro to millimeter sized reactors that we're typically using here. And then we're able to profile a volume within a reasonable time frame for solid state change. And here we're looking at changes before and after. So you can just see the distribution of these materials, which we've identified from this technique. And then when we do some reactions, so partial oxidation of methane, we can see, for example, the nickel oxide is reduced to nickel metal, mainly at the top of the sample, but there's still some nickel oxide at the bottom. So we're able, by doing this kind of profiling over the period of 1 hour, we can see a difference in the composition of the material and then relate that back to catalytic performance. Now, the neat thing is here is that nowadays we're able to screen over 1 million diffraction patterns within a reasonable time frame. How has this been employed? Well, we have a collaboration with BP, who form part of what's known as the Fulcrum Bioenergy Consortium. At the moment, they are involved in a development of a plant, which is actually dedicated towards creating sustainable aviation fuel using this reaction called Fischer-Tropsch. So what they're doing is effectively decomposing rubbish, and they're taking off the CO and the hydrogen, known as syngas, and then they're turning this into Fischer-Tropsch. And here's an example of Fischer-Tropsch diesel oil here versus the standard sort of diesel oil that's come from oil refining. And you can see here that the purity of this Fischer-Tropsch oil is far greater quality. It burns more easier. It has less emissions, less noxious emissions, because it's produced in this, let's say, more clean way using this technology. Now, we're not directly involved in this work, but we are providing underpinning information. So we're taking some of the catalysts that they use in the industrial reactor, or model catalysts, I should say, using the industrial reactor. And we're actually looking at the distribution of the key component in here, which is cobalt metal. So because they're using these types of material on a large volume, they're not using micro scaled quantities. They're now using kilograms of the catalyst, and these need to be preformed into millimeter sized objects. And we can apply this X-ray diffraction imaging technique, and we can look at what happens as you reduce the sample and then start to carry out reaction. And as you can see here, looking at these representative cross sections, we can sort of see differences in color. So you start to see, for example, one of these phases at the beginning disappear under activation, under reduction conditions, and then start to reappear again during reaction. And this is not good, because we're able to kind of control the environment. We can see that during reaction, we're starting to see this recovery of this oxide phase, particularly at the periphery of the sample. So this is just a summary of the total different forms of cobalt in the sample as we do the reduction and oxidation. And again, if we just take a sum of the total signal, we can see that the oxide phases increase as we carry out reaction. And that was a key finding here, that we can actually see that there's a buildup of those oxide components. Well, in fact, it turns out there's a buildup of the metal components on the outside, which actually become oxidized during reaction. And so we can come up with models like this to sort of say that actually these species on the outside become oxidized, and actually they're not very good for reaction. They're not giving us our sustainable aviation fuel, which in this case would be hydrocarbons. They are actually producing just methane. But the good thing is that when they produce methane, they also produce water, which leads to their reoxidation. So what you see is that the methane trace and our catalytic test spikes because of those small particles at the periphery of the sample, but then they become oxidized and they stop carrying out the catalysis that we're interested in. Whereas the elements that we are interested in particular, in this case, the higher hydrocarbons, are actually stable. To deal with these large volumes of data, the good thing with Finden is that we are eligible to apply for funding from various sources as a small, medium enterprise. A collaborative project, again, with UCL has enabled us to apply machine learning to squeeze the data processing time down from a matter of several hours, even months, of these large volumes of data. Remember, I said we had something like 1 million diffraction patterns, into now a matter of minutes. So basically what I have here is just some what we call ground truths. So when we carried out this analysis of 1 million diffraction patterns, we carried out sequential analysis. So each of the diffraction patterns was analyzed having fitted one, and then you kind of use that as a base fit, and then just extrapolate to the remaining 999,999. And you can actually get a ground truth for all the components. And you can then use all of that information, those observations, to train a machine learning algorithm. And what we can sort of show here is that we have a very, very faithful representation of the real system. So the difference between what we sort of determine in the standard fashion and what the machine learning algorithm has been able to determine is very accurate to within a very, very high degree. So as I mentioned before, if we then extrapolate this over large volumes of data, we can see that we can make significant time savings. And of course, as you can imagine, if this is taking us several hours to conventionally squeeze these data, when we're actually doing measurements at a synchrotron where we typically run for 2 or 3 days, it would then not be possible to analyze data in real time. And of course, to drive the experiment, and hence this particular application, machine learning, we think is very powerful for effectively enabling our business, but also enabling us to produce scientific output, which is actually a good way of highlighting some of the research that we're doing and our capabilities. One of the things that I think is very important about the Harwell campus is the opportunity to carry out experiments that you did not even consider possible. And that's not because you didn't even know that there was capability there. And I think in particular, the Catalysis Hub, which is a national initiative in catalysis, which is based at the research complex at Harwell, based on the Harwell campus. We were very fortunate to be located next to the central lasers facility. And traditionally, lasers for catalysis research has perhaps been underexploited because they're two quite different communities. But in collaboration with the central laser facility, we recently demonstrated how we could use their capability to shed light into the performance of zeolite catalysts that are used for this reaction of converting methanol into hydrocarbons. So we've just effectively taken our catalyst testing setup and put it onto a high-powered laser, which has actually got a very neat way of using time-gated pulse to switch effectively a liquid crystal display to change the polarity of the Raman signal, and to then use a polarizer to cut out the fluorescence. So the fluorescence is normally a big problem for measuring Raman spectroscopy on powders, but using this setup, you can remove that and get much better quality signal. And then we can see, for example, that as we're carrying out some catalytic experiment, so we're looking at the conversion of methanol as a function of temperature on a porous zeolite material. And what you notice here is there's this dip in the methanol uptake. So the samples are consuming methanol at this point here, but suddenly they stop consuming the methanol. And then we can actually look at the Raman spectrum evolution with time. And a key thing we notice here is this band here at 1551. And this allowed us to actually identify that, yes, you know, we see some of these other components here that are necessary for converting the methanol into the hydrocarbons that we're interested in. But actually, a key thing at 1551 are these species here, which are known as polyenes. And these polyenes actually block the active sites of the zeolite and stop it working. And a good thing, again, about the Catalysis Hub is that we have the opportunity to collaborate with experimental and theoretical or computational chemists. And the good thing about this collaboration was we could not actually identify some of these Raman bands without spectral simulation. So, for example, some of these species here are very difficult to measure experimentally, but they can be simulated. And the correspondence now between simulation and experiment is very, very powerful, such that we can even use, ideally, we now have a project trying to use these observations to predict topologies of zeolite that don't deactivate in this way. Finally, just a few words really about where does this in situ operando approach sit in the current thought processes, let's say, of catalysis researchers? Well, very handily, I have this diagram here, which shows that in this depiction, at least, it stands central to all the elements you would say are kind of fairly standard kind of aspects of catalysis research. It's not that it's so much underpinning, it's just, if you look at all of these initiatives, these are global initiatives around mainly the US, but also like Switzerland, the Netherlands, and even South Africa. The use of in situ and operando approaches has become central. So the idea is that it's very difficult for us to design a catalyst or prepare a catalyst at this point and then study it just by simply measuring in a lab under very simple conditions. It's very difficult to then understand with catalyst testing how you actually effect a better catalyst or understand how you can improve its performance. So these observations are key, because we can then sort of see what changes when it matters. So hopefully in the examples I've given you today, I've been able to show there's been a change in a spectrum or a pattern that coincides with a particular uptick in activity or downward turn in activity. So this philosophy, I think, is very key now in perhaps the leading initiatives on catalysis research. So there's always an element of in situ and operando characterization. But of course, you know, it underpins the whole aspect. No one of these aspects alone is sufficient to develop new catalysts and new catalytic processes. And it's acknowledged because actually the facilities, the X-ray facilities, for example, Diamond 2, so Diamond is going to be upgraded in 2025. There's a large consideration for the importance of this. So it's very much on the roadmap. So providing in situ and operando capability is absolutely critical for effective new catalysts for the future. Of course, increased brightness of sources does give multiple benefits. So effectively, we can collect what I hope that you've seen today, particularly in the X-ray diffraction imaging, is hyperspectral data. So the hyperspectral data here is kind of not only are you getting a spectrum at one point, but at multiple points as a function of time. And of course, this can give you so much more information on understanding why catalysts work and why they don't work. But of course, there are challenges in this. So we're going to have this big challenge of how do you squeeze all of this data and extract something more meaningful. And I should like to highlight that there are opportunities for scientific service providers in this regard. So what you find is that synchrotrons are very good at providing a national facility, and companies know what they would like to learn about their systems, but not necessarily how. And actually, that's where Finden has demonstrated that there's scope and opportunities here. But actually, with more facilities, with increased brightness, there's going to be more opportunities. So this is a time, I think, for scientific service providers to assist here. And finally, I'd just like to thank a lot of the people who were involved in this work, both from my section of the talk and from Richard's section of the talk. And finally, thank you all for your kind attention.
Thank you, Andy and Richard. We've got some time for some questions now. So I'm just going to have a look at Slido, and there is still some time to submit questions. So if you've got anything, please do. So coming on to the first question, I guess this is for Richard. How viable are CO2 capture techniques?
I think if you look at concentrated sources, for example, like a power station, there are really quite effective CO2 capture technologies. I think the real challenge is going to be developing viable direct air capture technologies. Now, there are air capture technologies, but how generally applicable they're going to be is, I think, still an open question. So I think one can actually be optimistic that if we can have sources of cheap sources of energy, then it will become possible to do direct air capture. But that's where I see the big challenge.
Okay. The next question, what role will catalysis play in hydrogen production?
Don't know when, Andy, you want to?
Sure, yes. Well, I think, catalysis can play a big role in this area. So I think, we're used to the different colors of hydrogen now. So I think blue hydrogen, where we're effectively using steam reforming of methane. I mean, this is clearly how we're mostly generating hydrogen at the moment. But of course, there is a push more towards the green sort of technology. So looking at, well, at least using sustainable methods to generate hydrogen in the first place, maybe from like water splitting using electrolysis. But there's quite a few different colors in between, depending a bit on the technology. But I mean, one thing is clearly important that we push for making these processes sustainable as possible. And that may mean that, you know, hydrogen, I think, is going to be as a fuel. You know, we have to think about carefully how best to exploit this. But there's lots of catalysis routes, let's say, to take you to hydrogen. You know, in fact, you could argue all of these processes for hydrogen generation involve catalysts at some point. And I suppose one of the other nice things with using catalysis to generate hydrogen is that they're often producing something else valuable at the same time. So if it was, for example, methane, you can actually split that into high purity carbons or even chemicals. Because I think that's another thing we have to bear in mind, is that as we move away from fossil fuels, we have to think about ways to generate the sort of chemicals that we take for granted every day that underpin this £227 billion industry. And I think catalysis can be absolutely essential for that.
Yeah. Okay, the next question, I guess this is to both of you actually. How important are techniques such as machine learning in the design of new catalysts?
Well, a brief answer, and thanks for the question. I think they're going to be very important. I mean, machine learning, for instance, is beginning to make major contributions to the whole area of computational modeling, including computational catalysis. But I think machine learning more generally will assist in the optimization of materials for catalytic processes. In fact, there's a group in Berlin led by Matthias Scheffler that has already demonstrated that you can optimize catalytic systems using machine learning. Very, very nice piece of work. So I think the answer to your question is it's going to play an important role. You know, how big a role, we don't know, but it's going to play an important role. And then pass over to Andy, because, I mean, your work showed how it assisted with the crucial area of data analysis.
Yeah, absolutely, Richard. I think that's right. I mean, of course, always the big challenge is training data sets.
Yeah.
But nonetheless, so I think with some types of problem that's a bit easier than in others. But nonetheless, it's clear that the proliferation of machine learning interest and capability is not for nothing. I think there are definite gains to be had here. And as highlighted before, I mean, you know, we've got increasingly more powerful computers to process data or to generate data. And of course, we have to think about how we're going to handle that. So we are almost, it sometimes feels as though, you know, the amount of data that we're generating is already a lot, and that's only going to improve. So I think, you know, machine learning, I see has got a very valuable role to play. And it's quite amazing how, in our experience, how generally applicable it was. And I think one of the things that we tried to do was try to push machine learning to do, well, we found it very, very powerful for prediction as well as, you know, sort of post analysis. So in other words, if we design pretty robust algorithms that are trained, can we then forward project the data such that, you know, we don't have to do the experiment?
Okay, so thank you for that. I guess, Andy, you've touched on this already, but yeah, so, you know, the techniques that you've been using collect a large amount of data. So how is this stored and analyzed, and is this process automated?
To various degrees, it is automated. There's always a certain element of human involvement, so they're not totally automated at this point, and that's partly because a lot of the systems we're looking at, we don't really look at the same systems over and over again. I think when systems are well studied, then I think, you know, you could say that there's an automation pipeline potentially available there. One of the things that we did with the diffraction imaging was, because you're generating so many images, that's ideal for machine learning. And there is, because we're not the only people doing this. There is infrastructure that take the raw data, and the first thing you've got to do is, because you're collecting an image, is to squeeze that down into a simple ASCII. And that, of course, is actually very computationally demanding. And of course, it does throw up the question about when we talk about making data available, which of course we're now obliged to do where possible. What form is that data in? Is it in the original form, or is it in the squeezed form? I mean, the good thing is the facilities have to deal with the original data, and we generally then tend to deal with the squeezed data. But that, again, is a bit dependent on the types of measurement we're doing. So sometimes you're getting data off the facility that's already in sort of an ASCII format. And there, actually, it's the processing pipeline doesn't need to be as automated. But, the plan is to try and automate these things as much as possible. And I think this is a general philosophy, let's say, at these national facilities, is that they would like to engage more widely with users. And of course, people have different experiences. So the more independent you make that analysis of, past experience, the more accessible it is. But then, of course, it throws up the question of, do you want people to treat it as a black box? But it's a balancing act, in my opinion. I think you need to enable people to use these facilities, but at the same time, they've got to know what they're getting out of it.
Okay, and then the final question that we've got, I guess this is for Richard. What impact do you think techniques such as quantum computing will have on catalysis research?
Again, it's a very good question. It's difficult to answer. We don't yet know the extent to which quantum computing is really going to have impact on computational chemistry and physics and materials. I mean, the computational catalysis essentially is kind of synthesizes those three areas. I think there is the prospect of very, very considerable impact. I think particularly in kind of optimization, in trying to predict the optimal structures of systems, quantum computing is likely to have a big impact there. It may have an absolutely enormous impact. We don't really know at present. There is a project, in fact, established by EPSRC, a collaborative computer project, which is exploring the role that quantum computing is going to play in computational chemistry, physics, and materials. And perhaps in 3 or 4 years' time, we'll have a better feeling. I think it's likely to have, it's almost certain to have an impact. How big an impact currently is, I think, is an open question, but it's a very good question.
Okay, that brings us to the end of the questions. I can't see any more in the chat. So I think we can probably say thank you to the audience for joining us, and also to our two speakers, Richard and Andrew. And just to say that the next lunch hour lecture will take place on Tuesday, the 18th of October, and it'll be entitled Weighing Trees with Lasers, New 3D Insights from Tropical Forests to Urban Churchyards. Thank you again for joining, and have a good rest of the day.
Thanks very much, Ms. Barr.
Thank you very much.